This video is based on the blog post Clean Code Horrible Performance by Chris. The link to the original post will be in the video description. Clean code, for the longest time, has been a concept peddled by schools, universities, and everything in between. It's an idea coined by Robert C. Martin, also known as Uncle Bob, which incentivizes creating layers of abstraction to make the code readable, understandable, and maintainable. Today we'll be focusing on debunking one of the design principles laid by this philosophy by starting with a program that implements the cleanest way to solve a problem and then slowly breaking down the rules, restructuring the code, and making it easier to understand from the computer's perspective. To make sure that we're not unfair here, we write a Rust version of the very sample clean code proponents use in their examples. This code creates structures for different shapes, and a trait, also known as an interface in other languages, to calculate the area of any shape object. It follows the clean code preference of polymorphism, where subclasses with shared behavior are preferred to branching conditionals like if-else or match. Here the subclasses are the shape structures like square, circle, etc., and the shared behavior is the area method defined on them by the shape trait. To benchmark the code, we'll be using the bench macro from Rust Nightly. Our benchmark is going to be incredibly simple. We create a list of 10,240 shape objects, and for each of those we calculate the area and add it to an accumulator. Running the benchmark gives us a baseline of 54,956 nanoseconds per iteration. Our friend Chris here found that we can improve upon this baseline with relative ease by modifying the code that performs the benchmark. Instead of using a single accumulator, we switch to using 4 accumulators and adding them up after all the iterations. This results in a performance improvement from the baseline by 3.1 times, that is 17,725 nanoseconds per iteration. Well, what sort of black magic is this? We'll get to that in a while, but for now, know that it's related to horizontal scaling with regards to the CPU. Looking at the code, we can see that due to the inherent nature of how polymorphism works, we're constrained to using this box-dyn syntax. I've covered how boxing values work in a previous video, but the gist of it is that these boxed objects, also known as trait objects or fat pointers, actually have 2 pointers inside them. The raw untyped data pointer points to the underlying struct allocated on the heap, while the other pointer points to the virtual dispatch table that maps the trait methods to the respective machine code. Obviously, this presents us with 2 layers of indirection to perform the lazy call to the area method on the shapes. First, we have to jump to the virtual dispatch table or the vtable from the pointer in the trait object, and then we follow the pointer in the vtable to reach the struct-specific machine code. Let's break the rule of preferring polymorphic code and replace the trait with the simple yet idiomatic use of enums and match statements. This type of conditional matching is prevalent in Rust code, and you might have even come across this pattern, with the only downside being if your code is a library. In that case, dependents of said library would not be able to implement the shape trait on their custom types, say a hexagon or an octagon. This design change shows a whopping 3.2 times performance improvement from the baseline to 17,141 nanoseconds per iteration. If we split the task among 4 accumulators, as we did before, we get a massive 8.5 times improvement to 6,434 nanoseconds per iteration. As Chris points out, the performance gains here indeed come from the removal of the box construct. With the shapes now being represented as enum variants instead of trait implementers, the compiler knows the size of each element in the vector. It no longer needs to create an intermediate trait object and then follow 2 levels of indirection during runtime. Let's crank this up a notch by using a lookup table-like construct, where the shape structure itself holds the width and the height as well as the multiplier for a specific shape. The concrete shapes are defined as the variants of an enum type. The constructor for the shape type ingests these variants and chooses a multiplier accordingly. For example, it would choose a multiplier of 1 for a square, a multiplier of pi for a circle, and so on. Nonetheless, it's not too different from the previous iterations, except for when it comes to speed. The code is 6.4 times faster than the baseline, and applying the 4 accumulators trick on top of it yields a program that's 11 times faster. Okay, time to address the elephant in the room. What's so special about splitting up the accumulator into 4 independent ones and then adding them up in the end? To investigate, we'll look at the resulting binaries under a decompiler, which will allow us to see the exact machine instructions the compiler generates for our code. I'll be using Radar 2 on my x86-64 machine. If you're following along on a different architecture, your mileage may vary. We run the mnemonic AAA to analyze all functions. Now that the functions are analyzed, we can proceed to list them and find the address of the main function. To do this, we'll use the AFL mnemonic, that stands for Analyze Function List, and then pipe the output to ripgrep to search for the main function. Okay, so we notice that the main function is located at the address hex 000086C0. We will print the disassembly of the function using the PDF mnemonic. Here we can notice memory allocations for the initial vector. The eagle-eyed viewers amongst you might have already noticed the while loop between physical addresses hex 88E0 and hex 8974. It's also conveniently represented by the dotted line here. We can notice that it's performing a conditional jump after comparing the RCX register with hex 2803, which translates to 10,243. This seems very close to our total object count 10,240, but why that extra 3? Well, because the compiler assigned 3 to the register and started counting backwards when indexing the shape vector. The compiler is way smarter than you and I. The real magic is what happens inside the loop. If you've ever reverse engineered software before, you might have noticed that instead of the move, add, or multiply instructions, what we have here are move SS, add PS, and mul PS instructions operating on weird looking registers that start with XMM. Turns out these instructions and registers are a part of the streaming SIMD extensions introduced by Intel in their CPUs about 2 decades ago. What is SIMD? It stands for Single Instruction Multiple Data. These instructions perform the same operation on multiple operands. For example, the highlighted instructions merge the multipliers for the 4 current shapes, with each value being represented by a single precision 32-bit floating point number. All 4 of them are merged into one giant 128-bit XMM register. XMM3 containing the multipliers is multiplied by XMM4 containing the widths. Next, we merge the heights into the XMM5 register. Finally, these giant registers are multiplied with one another to calculate the areas of the shapes. The 4 accumulators are also a part of the XMM0 register, to which the areas are added. The takeaway from all of this is that multiplying 4 of these numbers in parallel using SSE takes the same time as performing one of the multiplications using regular instructions. The portable SIMD documentation for Rust states that SSE is enabled by default for x86-64 targets. Rightfully so. It makes a lot of sense considering it was introduced 2 decades ago. Practically every desktop computer in use has this functionality built right into it. There have also been more recent improvements in SIMD extensions such as Advanced Vector Extensions, AVX, and AVX512. Obviously, we can't assume that all machines support these extensions, and being less mindful when enabling extensions can actually make our binaries less portable. As for ARM CPUs, there exists a SIMD extension known as Neon, all uppercase, but this is not enabled by default. So, how does clean code fit into this picture? It doesn't. In fact, the use of SIMD with the clean code version still had to go through layers of abstraction instead of being able to directly access the floating point numbers. Separation of concerns can still be achieved by other means, such as moving code related to a specific functionality into its own module or crate. The powerful idea of namespacing can promote separation of concerns while preserving locality of behavior. With all this said, this is not aimed to be a dunk on Uncle Bob. I think he has some great insights. You might want to watch him getting interviewed by your local Vim enthusiast. Alright, so that's all for now. I hope you learned something. As usual, sources and the code to render these animations will be linked in the description. Thank you, Chris, for letting me make a video based on your blog, and until then, I'll see you around.